Welcome back. In this video we're going to take a look at a couple of theorems involving intervals, and they are the extreme and the intermediate value theorems, both of which are fairly interesting in their own right. So the first of these is the extreme value theorem, and what it says is that if we have a function on a closed interval that's continuous, then it attains a maximum and a minimum value. Okay, so that is to say that there are actually maximum and minimums. There aren't just supremums and infimums, or a supremum and an infimum. And so it says that we actually have a maximum and a minimum on this interval. Okay, so to prove this, we're going to attack it a slightly different way. So we'll prove, let's just figure out what we know so far. First of all, we know that f of ab is bounded. Okay, we did that last time. A continuous function on a closed interval is bounded, and bounded sets have supremums and infimums. So has a supremum and an infimum. So we'll just focus on one direction. So we'll just look at the minimum value, but you can use the same argument to find the maximum as well. So I'll let m be the infimum of our set of function values. Okay, now remember from earlier on in the course, if our function attains its minimum, then that minimum has got to be equal to m. Okay, so remember that if there is a minimum, then it's always equal to the infimum. So if f has a minimum, let's just write that more correctly, if f of ab has a minimum, it must be m. Okay, so i.e. there exists an x naught such that f of x naught equals m. So we're going to do this by contradiction. So we will assume that there is no minimum. So we're going to assume that f of x is greater than m for all x. And what we should hopefully try and find somehow is a contradiction here. So we're going to work it like this. So if this is true, then f of x minus m has got to be greater than 0. So we're going to take this and we're going to take the reciprocal of it as a new function. So let g of x equal 1 over f of x minus m. Now why would we do that? Well, if we're assuming that f of x minus m is positive everywhere on the interval, then this function here that we've just defined is also going to be defined everywhere on the interval. And so it'll be continuous, and it will therefore also be bounded. So g of x is continuous, and hence g on the closed interval is bounded, because it's not going to be equal to 0 at the bottom of that fraction, so we're going to be fine. Okay, and just like we did before, this time we'll take the supremum of this set and let S be the supremum of G of AB. Because we're taking the supremum now because we're going to flip it upside down again in a second, and that will put it back down to the minimum end again. Therefore, let's write down what we now know. We now know that G of x is between 0 and we know that's equal to 1 over f of x minus m, and S for all x in our interval. Okay, and what we can do now is we can take the reciprocal of this whole thing and reverse the direction of all the inequalities. So this will give us, therefore, 1 over g of x. So now we've got a statement about our original function x equals f of x minus m is greater than or equal to 1 over s, which in turn is greater than 0. Okay, i.e. f of x is greater than or equal to m plus 1 over s. Now here's the trick. This makes m plus 1 over s a lower bound, but m is supposed to be the infimum, which is the least lower bound. And there is our contradiction, i.e. m plus 1 over s is a lower bound for f of x, or for f of ab if you like, contradicting m being the infimum. So what assumption have we specifically contradicted here? Well, the infimum comes from the boundedness of f of ab, so that's not the assumption we've broken. The thing we've broken is this one here, the assumption that f of x is greater than m. Okay, so that m is just the infimum and not the minimum. Hence, there must exist, or hence m must be the minimum. Let's try spelling that again. Of f of ab. Okay, and we could use an identical argument to show that f of ab has a maximum as well. Again, we'd set the supremum equal to some letter, and then we'd go through the same exercise and show that the supremum must in fact be the minimum, because if it's just a supremum and strictly greater than everything in our set, then that will give us the same kind of contradiction. Okay, so here is our next theorem. This is the intermediate value theorem. And this one is quite simple to state, but it's even simpler to possibly just draw a picture of it. What it says is that if I have an interval a and b, and I have a continuous function on this closed interval, so here it goes. It's continuous, so it includes the endpoints. So just mark those in. Then this value here is f of a. This value here is f of b. What the theorem says is that if I have another value L, which lies between those two, now we could write f of a and f of b the other way around if we liked, but for our purposes of our argument, we'll just take this case here. Then there exists a point C such that f of c is equal to L. You could see that we could simplify this slightly by shifting the whole thing down a wee bit. So if I instead just move these down, I define g of x to equal f of x minus L, then the same picture shifted down will look a bit like this one here. My point C will be here, this will be g of a, this will be b here, and this will be g of b. Okay, so it's kind of convenient to shift our whole thing down so that g of c is equal to 0. So the intermediate value theorem says if I have f of a, f of b, and a number L in between, then this point C exists. Or alternatively, this point C, which is the same one, exists such that f of c is L or g of c is 0. So we'll prove it using this case as our starting point, and we're going to use our nested intervals to make this work. So we're going to limit ourselves to the case, assume f of a is less than 0, is less than f of b. We seek c such that f of c equals 0. The other case follows pretty straightforwardly from this. Okay, so what we're going to do is we're going to start using a kind of bisection method to create a whole lot of nested intervals that are going to hone in on this point. So let's just sketch a little picture of what we're attempting here. So we've got our points a and b, right? And these will make and we know that our function is below 0 here, and we know it's above 0 here. I'm going to actually draw this a little more exaggeratedly, maybe like that. What we're going to do is we're going to define our first interval to be a to b. So this, we'll call this a1 and this b1. And then we're going to find the middle point, and we'll define b2 and a2 such that we've got a negative value on the left-hand side and a positive value on the right-hand side. And then we'll find the midpoint again, and this will be, let's change colors perhaps, a3, sorry, b3, because on the right of it, and a3. Okay, so we're going to create a sequence of nested intervals AK or AN BN such that I guess the size Bn minus An equals B minus A over 2 to the power of n minus 1. Okay, so, and f of an is less than 0, and f of bn is greater than 0. Okay, so at this point in time, we've set ourselves up a sequence of nested intervals that has size going to 0, according at this rate here. And we're guaranteed that we're always choosing our A's and our B's so that we get a negative value on the left, so f of an is negative, and we're getting a positive value on the right. So the nested interval property tells us that there is a point inside all of these, and we're going to assume for sake of argument that the f of that point is non-zero, although this will actually provoke a contradiction. So by a nested interval property, there exists x star in our interval such that an is less than or equal to x star is less than or equal to bn for all n. And we're going to assume that there is no point in AB with no point C in AB with f of C equals 0. So hence f of x star is not equal to 0. Okay, and let's just, without really losing any generality, let's assume that f of x star is positive. Okay, so this is we're going to attempt contradiction. This is our assumption that we should hopefully find results in a contradiction. Okay, so if we were to now zoom in on our picture a wee bit, we're assuming that g of x star is positive. So if we were to zoom in a whole lot, here's x star, this is g of x star over here. Okay, now's where we need to think about the sequence of intervals we've just created. Our function is continuous. That means we can specify an epsilon band around g of x star so that if I force that there exists a delta, so that x star minus delta and x star plus delta, if we choose this epsilon small enough, if we choose this value of epsilon small enough, then we can force the function, the function over this whole interval x star minus delta to x star plus delta to be positive. So if we, for example, choose epsilon equal to g of x star itself, that would be pushing this band down to here, maybe up to here, then there exists a delta so that if x is between x star minus delta and x star plus delta, the entirety of my function is going to lie up here above 0. So because g is continuous, there exists delta greater than 0 such that absolute value of g of x minus g of x star is less than epsilon, and the epsilon that's convenient for me will be a g of x star. You could make it g of x star over 2 if you want to really push the point home and squish the function into this band here, but g of x star will do the trick, and that in particular implies that g of x is greater than 0 for all x satisfying absolute value of x minus x star is less than delta. Okay, so the stage is set now for our argument. Remember that our sequence that we developed has a size that converges to 0. If we consider the sequence of interval sizes, this converges, which means that we can find a natural number n such that the sequence, the length of the interval surrounding x star that we come up with is small enough to fit inside this x star minus delta, x star plus delta region. So in particular, we can make it so that bn minus an is less than delta. So the length bn minus an is less than delta, which means it must fit somewhere inside this bracket here. So because bn minus an, treated as a sequence, converges to 0, there is an n in our natural numbers such that bn minus an is less than delta. This implies that g of an is greater than 0 and g of bn is greater than 0. Okay, so if I were to find this an and bn here, then it's supposed to be the case that gn, why have I called it g? Sorry, f, these should all be f's. I've confused some notation here, apologies for that. Let's just tidy this up. These should all be f's. Hopefully you haven't lost the thread of the argument there. You may want to just go back and read through some of these just to double check. Replacing all the g's with f's. This is the g from the previous slide. Sorry about that. If I get time I may redo this, but otherwise you'll be stuck with it. This implies that f of an is positive and f of bn is negative, is also positive, but we've already assumed that f of an has got to be negative. So here's our contradiction. We've got f of an is negative here, f of an is positive here. That's a contradiction, and so our assumption that there is no point C is false. Our assumption is false, and there exists C such that f of C is equal to 0. Okay, apart from my notational issues, that's hopefully not too bad. So what we did is, first step was we created some nested intervals that honed in on the 0 of this function. Okay, so we always took the left-hand side to be negative, the right-hand side to have positive function value, and we took our intervals such that they halved in size each time, which in particular means that the length is a sequence that converges to 0. We then assumed that our function value, again there should be f's over here too, let's just fix them as well, there should be f's. We then assumed that our function value was not 0 at this point that was in all the intervals, which without loss of generality we could assume it was positive. But then continuity meant I could find a delta that meant the entirety of the function was above 0 for x within delta of x star. And then I just shrunk my intervals small enough so that they surrounded x star and were inside this delta band, and that forced both endpoints of my interval to both be positive. And that was the contradiction that we were aiming for between these two facts here. And once we found that contradiction, it means whatever the thing we had assumed must be incorrect. And that was that there was no point C that existed with f of c equals 0. Okay, so we found a contradiction. That means that assumption was wrong, and therefore there is such a C, which is what the intermediate value theorem was wanting us to prove. It's not too difficult to do the other cases where you have a function perhaps going downwards, and you've got f of a is bigger than L, is bigger than f of b. And so I'll leave that one as an exercise, and we'll catch you next time.